So a couple of weeks ago, I was in Germany contributing to Porsche's bottom line. And part of the deal was that they gave us a tour of the factory. And it's a spectacular place. I would love to have shown you a photograph of the inside, but they stripped us of all of our cameras before we went into the building. And what I learned, which surprised me, was that Porsche doesn't make cars. It designs them, it gets other people to build all the bits, and then it assembles them. It's primarily a design and logistics company. It is spectacularly successful at that. And one of the reasons it's successful is because it does what it does very well. And the other reason is because for every part that it sources, it has about half a dozen suppliers who are best in class competing for its business. So it's able to take advantage of all of the manufacturing expertise that is available in all of its suppliers in order to be able to build the things that are really fun to drive around the country. So what I thought I would do is I would spend a little bit of time talking about how cloud providers like Google and Amazon and Azure and people like that go about trying to compete for your business as best-in-class suppliers of technology from behind the scenes. So time is short. I can't talk about everything, but I chose to talk about 3 particular things. The first of these is how do we think about managing and making sure the capacity that you want when you want it is available. So we all know and love this illusion that there is infinite capacity in the cloud and you can get arbitrary quantities of it whenever you want. You show up, darken our doors, and demand enormous quantities of computation. Let me tell you how wonderful it is when you have it. One of my colleagues was doing some experiments for a research paper that we were working on, and we looked at later about how much computation we were using, and we discovered that there was a moment when we had allocated ourselves 200,000 CPU cores. And we hadn't even noticed. It just worked. That gives us the freedom to focus on the stuff that we think is incredibly important and matters, because having to worry about how do you get those 200,000 in order to be able to get a result that you can get to a paper with a deadline that is pressing on you is really hard to do. Papers don't have very big, important things. If you worry about businesses, those really matter. So what does it take to make that happen? Well, systems like the one in this picture, this one happens to be in Lithia Springs, systems that page their operators with an emergency message to say, we are down to the last few petabytes of free space. If we're going to provide people like yourselves the chance to show up at any moment and get whatever you like, we have to make sure that we have slack and the right places at the right time, and that we have time to adjust to the fact that we're maybe running out of something. And at this scale, it turns out that one of the things that is most important is systems that worry not about performance, but of course that matters, but more important than performance is failures. At scale, you experience every bizarre event type. Annual failure rates of disks and processors and OS upgrades, whether they need it or not, happen all the time. So it is perfectly normal to run in a world where machines are being recycled or rebooted roughly once a month or so. But also the lunatic fringe of things like, turns out wild dogs like to chew on cables because they like the taste of the grease that you use to pull them through the conduits. Sharks react positively to the electromagnetic fields that come when you put undersea water cables that have the electrical power required to power the repeaters. Most people dig fibers deep enough so that you don't have problems with them, but it turns out when you're burying a dead horse, you need a really big hole. So you have to be able to cope with the one in a whatever events for this kind of environment. And if you find yourself in a world where you're doing really large-scale systems, which is what the cloud providers that basically have been doing for the last decade or so, you end up spending almost all of your design time worrying about those corner cases. I used to be at HP for about a quarter century, and we were very proud of the fact that we would provide very performant storage systems. We were working our way up towards a petabyte scale system when I left. When I got to Google, it turned out that the design discussion completely flipped. The first question in the design discussion is, what happens when that fails? We can always make it faster. We know how to do that. We throw more machines at it. But what happens when that fails and that happens? Think about the corner cases because you're going to experience them. For example, a moderate scale installation of a system like Google Calendar, one of the instances maybe have a couple of thousand machines involved in it. That will be experiencing 10 outages a day. It's perfectly normal, right? It's not something you need to panic about. It just happens, so get used to the idea. It's perfectly normal and it's okay if you plan for it. So what can you do to plan for it? Well, there's a bunch of stuff, right? The first thing is that you mustn't get attached to any of your programs, right? People have use this analogy, cattle and pets. Your programs are not pets in this environment. They're cattle. You lose one, you make another one. bring up the next one because it's ready to go. You'll find ways to bring things up quickly, so you don't have large amounts of state embedded in individual copies of them. You use external state that is replicated and resilient, so you can get fast restarts. You worry about making sure you have complete copies of them in one data center and another, so that if one data center goes down, or some drunken hunter shoots the telecom connection to it, you can still get access to that stuff. The good news about this is once you start worrying about those kinds of failures and you build all of the support for that stuff into your system, you end up with amazingly resilient systems, which is good for us because it means we have a very, very small number of operators for each of these systems. And it's also good for our customers because they don't have to spend too much time worrying about it. They don't worry about it because it's normal to have this kind of behavior. And this is a very completely different attitude that you need to embed in your application developers to think about this kind of stuff. It's not a panic situation. It's, yeah, we've had another one. OK, great. Once we've got it up, and we can keep it up, then we start worrying about how do we make it more efficient. And this is where we're motivated, like you are, to try and deliver sort of the Moore's law price reductions to you as customers. But how do we do that without, we have to make sure we don't get excess wastage. So this happens to be a graph of some virtual machines packed into one of our cells from mid-2014. So there are two graphs here. One is showing CPU allocation and one is showing memory allocation, and they line up. The vertical lines actually correspond to the same thing. So it's virtual machines, its CPU and its memory allocation for the same thing. And you see the white space at the top. White space is bad news. That means we have stranded resources. We've either filled up all the CPU and left memory behind, or we've filled up all the memory and left CPU behind. Well, we looked at this and we thought, this is actually, I think, a rendition of our current system. We went, this sucks. Right? We can probably get another few percent of performance efficiency here. Well, a few percent performance efficiency, that's not such a big deal. Well, actually, for us, it's another data center. It is a big deal. So you've got people who are operating at this kind of scale who worry about those kind of things because then they can pass those savings on to other people because we're competing with the other people who are playing the same game. We expect them to be doing the same. The other thing we can do, this is actually a graph for one of our internal workloads. So this is some data that I published in 2011. We took a snapshot of every single job that arrived, every single task placement that we did, and the 5-minute usage information for every single one of those tasks on a median-sized cluster for the month of May 2011. A median size for us was 12,500 machines at the time. So x-axis is time, y-axis is usage on the left-hand side, and allocation on the right-hand side. The pink stuff is for processes, again, these internal loads, not external VMs, processes that we guarantee will have resources if they show up and want to use them. As you notice on the left-hand side, most of the time they don't. And that's perfectly reasonable because they have provision for the second time Michael Jackson dies. But that excess capacity that is not being used is a waste. So what we do is we recycle it for applications, particular things like batch jobs that can cope with stuff disappearing under their feet while they're running. And you'll see that the black and the green here represent additional batch jobs that can run on top of this stuff with lower quality guarantees about access to resources. And in fact, because we're playing statistical multiplexing games, we can allocate more than 100% of the resources in the cluster. That also reduces the costs. Now, we don't currently do this for our external VMs. We may come back to that. And then one last graph about what our sort of workload looks like, because I want to emphasize that we've been living, we and other people have been living in a world where we have been handling heterogeneous workloads with all sorts of bizarre behaviors for a very long time, and we've got pretty good at handling them. My expectation is that the external world will be imposing demands on the cloud that are going to look more and more like the internal demands we've been seeing for some time on the cloud. So for example, here this is a cumulative distribution function of execution times for a job. So a job is something you show up and I say, I want to run this, get started, and it'll run for so long. I want 400 copies of a task. The x-axis here is running time till it finishes. It's a log axis. Notice that some things never finish. That just meant they ran over longer than 29 days. So those are the long-running services, the things that offer stuff like Google Docs and Gmail and things like that to the outside world. But there's lots of things that only run for a few minutes. Those are typically the batch jobs. So we pack lots of those things into the spaces left behind the big boulders, which are typically the long-running service jobs. So those are the kinds of optimizations we've been trying to work on for the last few years in order to make our efficiency higher, to reduce our costs so that we can pass on to people like yourselves.